Dear my student, we have finished calculate the slope and the deflection of the beam by using the conjugate beam already. And now we are going to change to a new method that's called the method of virtual work, or in another name is called the unit load method. That's method of virtual work is very versatile. It can be used to determine the displacement of the truss, of the beam, and of the frames. This is one of the most powerful methods that we are going to learn in this course. However, the virtual work, they says by the name of the method of virtual work. That means we are going to talking about the work, and if you may recall from your previous knowledge, what is the work? If you have a weight, okay, of mg, and then you like to move this for some specific point up until here of the height of h. So the work that you going to move this is going to be the mg, and then time h, okay, and then this body gonna have the energy, okay, it's going to have the energy of mgh, okay. However, when you move it by upward, that is in the opposite direction of the mg, so the work is going to be the negative in this case, and the energy is going to be in the positive. That means if you release this body is going to drop down to its reference points, okay, by releasing the energy of mgh. And by doing this, we may conclude that the work is going to be the force times the distance. And also, if you have the moment, the work going to be the moment times the rotation or the slope, okay. And in our real world, there is a principle that's called the principle of conservation of energy. That means what? That's if you perform the work, okay, moving this body by the distance of h, and it will collect the energy of mg minus h, okay. This work gonna be equal to energy that's stored in this mass, okay, of mgh. The energy, external energy, is also going to be equal to the work, okay, external work, and it's applied to the structure. For example, the truss here, this is the truss, and before the application of the force, the truss have the shape like this, and then when you apply the force to the truss change the shape, okay, and then the point that you push the truss, you're going to move your finger about this, and when the force that you apply times the deflection, that is going to be the external work, okay, that you apply to this. But this external work is different from the rigid body work, okay. For the deformable body work, is called deformable body work, the work of deformable body. Let me just put it, the work of, this is going to be work of deformable body, work of deformable body. Over here is the work of rigid, okay, body. Work of deformable body, when you push it with the force of 0, okay, there is no deformation here or deflection here. When you put it for 1 unit, it's going to have like a 1 unit of force is 1 millimeter, 2 unit of force 2 millimeter, 3 unit of force 3 millimeter, and 4 unit of force you get 4 millimeter. Okay, that means you're going to get the linear. Okay, for this is the linear relationship of the force and the deflection, and then you get a graph like this. Okay, so the work that you will form here is going to be 1/2 of the F times V, and we can prove that later. It's going to be the area under this. And this external work going store in the structure, going store in the member that get elongation on the top, and in the bottom chord. Let's say this is bottom chord, for it shortening, top chord going to be in what's so called elongation. Okay, and then the diagonal also. See, when it's shaped like this, so the energy that's stored in the member, the work, actually is going to be work. That's changed to be the energy store in Truss member is going to call the strain energy, because it's going to store due to the deformation. Okay, due to the strain of the member. Okay, and this is going to be the what's so called the internal work. So following this principle, we can explain by using this example. For example, when we have the truss in equilibrium, and then you push the truss by a force of F, and it's still in equilibrium. Okay, you got the external work, and external work gonna make the truss deform like this, and the deformation, okay, gonna hold energy or store energy as the form as the strain energy, in which the external work going to be equal to the strain energy. Okay, and if the relationship of the material is linear, okay, the U sub E will equal to U sub I. Okay, one thing that can prove the energy that's stored in the member, if you have your like a plank of wood or a ruler, okay, and you just bend it, okay, you may bend it like this, and when you take the force out, the ruler going to return back to its original horizontal length, right? That means when you bend it, it stores some strain energy. It store strain energy. And when you release it, when you release the force, is release the strain energy, and then the store strain, SCAIN, okay, strain energy, the store energy and the release energy, they are going to be equal. Okay, and the external work, okay, like I said, for the deformable body, the external work, when you start by taking the lab number 2 of the material testing. If you remember, we have what? We have a rubber band. And then we put the rubber band by putting the weight. From the start, you can get the relationship between the force and the elongation is 0, 0. When you put 50 Newton into the rubber band, into the rubber specimen, what happens is it's going to get some elongation, like that is going to be 5 millimeter per se. If you push it to 80 Newton, you get 8 millimeter. And then you put it to 100 Newton, you get 10 millimeter. Okay, so that is going to be 5. This is maybe 8. This is maybe 10 millimeter. So the force that you apply gonna be like a 50 Newton, 80 Newton. The relationship of the behavior of the rubber band, rubber specimen under the lab is linear elastic. So you get the relationship between P and X is linear. Okay. When the external force, cause the elongation, dx in the direction of the force, we will have the small external work due to the force F. Let's say this is going to be the force F, and then it's going to cause some small elongation dx here. So the energy or the work that's produced here is going to be F times dx, which is the area, inside this. If the force is increased, from 0 to P, and the elongation increase from 0 to delta, if it was from 0 until 100 Newton, for example, and this from 0 until the 10 millimeter, this is, let's say, millimeter, this is going to be Newton, this is going to be 100, and then you get the graph like I draw to you, and you may have the total external energy that's caused by the force F equal to the integration of F dx. And for linear elastic, you may have F equal to Kx, and then you put it over here. This is going to be the integration of Kx and dx. This is going to be Kx squared over 2 from 0 to delta. And then you may get this one as 1/2 Kx delta, 1/2 Kx delta squared by integration of this function. And let me just put it up like this. That is going to be the 1/2 K delta squared by this equation. And then if you have to put back again, F, the K delta is the P. So you got this is 1/2 P delta, which is what? Which is the area, under the graph. That means for the linear elastic, when the load increases from 0 to P and the deflection increases from 0 to delta, the external works due to the force is 1/2 P delta, which is the area, the green area shown here. However, if there is something that causes the material of this member elongate by the small amount of delta pump, this is similar to the yielding. This is similar to the cost of yielding when the force didn't increase, however the elongation increased. And then what we have is the work due to that increments of delta pump is going to be just the P times delta pump, which represented by the area here. Just the term P and time the length here is delta pump, is area here. Again, for external work due to the moment, when the system, maybe it have the spring here, and then this spring has stiffness of K and is subject to the external moment M, causing this rotation by dx. So the external work is going to be the same thing if you plot the graph of M and theta when the moment is 0. We start here with the 0, and let's say this is in radian, and this is maybe in Newton meter. And then if you push the moment a little bit more, just say 1 Newton per, sorry, no, Newton meter, and cos this one like a 0.001, and cos this is 1, and if you put it 2, it's going to be 0.002. If you put it 3, it's going to be 0.03. So you get the relationship the same as before. And now you have the relationship of m, okay, equal to k theta and theta. That is showing the relationship between the moment and the theta by this graph. And anyway, if you have the moment m, okay, m is here somewhere, moment is m is here, that's cause the small rotation here of dx. So the energy due to the moment m causing the small rotation dx is going to be m times d theta as this one. Okay. If m is increased from 0 to m, like I said, from to m, okay, and then this is from 0 to theta. If you increase this, and you will have this for u sub o equal to integrate m d theta, okay, and m equal to k sub s theta. You just put into this. So this is gonna be k, okay, k s theta d theta integrate from 0 to theta. So this is going to be what? Ks theta square divided by 2 from 0 to theta. And then you may have what we have before. Let me erase this. That is going to be 1/2 of ks theta square. And then you get this at the energy of at the external work due to the moment. It's going to be 1/2 m theta. That's going to represent the area under the graph that I just erased. And again, if there is something that's caused the rotation increase by theta pound without the increase of m, so the external work or the extra work due to that moment gonna be m times theta pound. Okay, and show the area as before. It's going to be the rectangular area, not the angle. And this is going to be basis for the development of the method of virtual work. It's based on what? Principle of conservation of energy. It's based on the external work due to the force, and also is based on the external work due to the moment. We just finished this discussion. Okay, now that is external work. Let's have some discussion on the strain energy that's stored in the member. Okay, and just for example, if you bring up the rubber band, you may have rubber band from 7-Eleven or some store, and then if you pull the rubber band maybe have the length of 5 centimeter, and you pull it to be the 10 centimeter, and if you release one finger, the rubber band will put back into your hand. Okay, and then you may hurt because the rubber band store the energy. When you release one of your hand, and then the rubber band will release an energy. When it's released the energy, it hit your hand and you may hurt. Okay, for our consideration, we start with the axial load member. The axial load member here is kind of what's so-called the two-force member, and this is going to be a kind of truss member. Okay, truss member. And our material that's used to build that member is isotopic. What is isotopic? The isotopic is if you cut this material in this direction and you test it, and you cut it in the ortho direction like this, and you test it, you're going to get the same property. Okay, the steel is a kind of isotopic material, but the wood have the grain. Okay, the grain of the wood. The wood didn't have the timber. Let's say it's a wood, it's a timber. Okay, the steel is isotopic. The timber have the grain, so the timber isn't the isotopic material because it has the property perpendicular to stain, different from those parallel to the stain. Okay, the property of the wood in these two directions are different. So the wood is not isotopic material, but still you can test steel any way you like. It will get the same property. And then homogeneous material. Homogeneous material, that means you can point to any point of this material, and then you got the same material. Okay, that means the steel also. The concrete not actually the homogeneous material, actually is composed of sand, composed of crushed stone, composed of cement paste. Okay, we are concentrated in what we have is the steel. Okay, but in mega scale, we consider the timber, we consider even the RC as the homogeneous and isotopic material. But that's macro scale, it's not micro scale, so we can consider it. We can consider a beam, the reinforced concrete beam as a whole, and when we consider it as a whole, okay, you cannot separate the difference between the sand and the gravel and the crushed stone. So it's going to be isotopic and homogeneous material. And also it has the linear elastic behavior. That means the relationship of the stress and the strain is going to be in the linear relationship like this. So this portion for the structural steel is linear elastic, and then it's come to the yielding and strain hardening and necking. So we only concentrated our consideration into only this portion, not go beyond this. This is going to be the portion of linear elastic. And what we have next, if we cut this material as this given point, okay, as we have here, and then you draw the free body diagram of this. This beam gonna subject it to the axial load of it, and it's going to produce the normal stress. Okay, and the stress here is going to be N over the area A. Okay, at the same time, this element going to be elongated, and due to this elongation of delta, so the strain is going to be delta divided by L. And when you push everything into this, it's going to be N over A equal to what E? The E is slope here, right? The E is what? E is modulus of elasticity. If you can determine it, you may recall back to the lab number 3 when we test the steel in tension. And then we can determine E, and then that is going to be the delta over L. You get the equation here, and now you may move for the delta. So the delta is going to be NL, N the force over here, okay, and time length L, and then divided by AE. That is going to be the elongation of the specimen. And now you may do the test again, and then go back to the lab number 2 or lab number 3. Number 2 is going to be close to, this is P, that is going to be this is N, okay, this is going to be delta, and if you plot the graph going to be linear like this. So the energy or work that's stored here going to be 1/2 N delta. So you can put this one back, and you can determine the strain energy that's stored in the axial load member. That's for the Truss analysis in the form like this. Okay. Now let's consider the beam. When you have the beam and then when you put the force here, this beam gonna have some kind of deformation. Okay. If you put it in something like this, not just only the line that's passing to the neutral axis, the beam gonna bend like this. Okay, and this portion of the beam that's used to be this gonna bend into the shape like this one. Okay, and you put here, and as you may know, you may cut this one, and you can determine the reaction here and reaction here, and this reaction when you cut here gonna produce the moments m here. So this moment, that is the one that causes the deformation of the beam. And if you go back to the elastic beam theory, okay, you have what? Under this, you have the deflection here, of phi, and then you have the slope. Okay, the slope here, the slope is going to be theta. The theta is going to be d phi by dx. And then you may measure the radius of curvature. And then you have d square phi by dx square equal to m over ei. This is the equation for the elastic beam theory. That we have it since the start of this chapter. And then what we have, if you put this, okay, into this equation, you may rewrite this equation to be as the d by dx, d what? D of the d phi by dx, putting here. So mathematically, you can write down this equation easily, and then you get this one equal to m over ei. And this equation gonna be d time what? Time theta, and then dx, and then equal to m over ei. And if you rewrite this equation again, you obtain this equation. Okay, and next what we have is putting it back into this equation that we have. Okay, and then if you put this one, you get the equation for the strain energy stored in the beam due to the bending, in the form like this equation. And since the deflection is the continuous function along the length of the beam, okay, it's going to be continuous along the length of the beam, and it's curved, so you need the integration to cover the whole beam. Okay, and what I'm just passing through this is also can be used not only to analysis of the beam, it also can be used to the analysis of the frame also. Okay, and we're passing through this from what we have now, from the principle of conservation energy into the external work due to force, due to moment, and due to the strain energy in the axial load member, and to the strain energy in the member that's subjected to the bending, which is for the beam and for the frame. Now, let me apply the principle of work and energy to solve some simple problem. Okay, and if you have a cantilever beam, when you have cantilever beam, that means what? This is going to be fixed. This is fixed, and this is going to be free. When this one fixed, what is mean? The deflection, okay, at B in the horizontal direction equal to the deflection at B in the vertical direction, and equal to slope at B, and all of them is 0. Okay, and for the free end, at the free end, okay, you may have the deflection at A. Okay, this one may be the deflection at A in the vertical direction. And actually, you have the deflection at A in the horizontal direction, which is going to be very small, usually, compared to the vertical, the deflection. And you also have this. If you do some kind of draw a tangential line to the point A, and you may have this one for the slope, and it's theta A. Now, we are only interested to determine the vertical. We are going to find the vertical displacement. Okay, at point and at end A of the beam. Now, for the principle of work and energy, from the principle of conservation of energy, the energy due to the applied force, which is external work, okay, is equal to each other. It's going to be the energy stored in the beam, which is the strain energy. By previous equation that we have, the external work going to be 1/2 P delta X. Remember, if you have the P here, delta here, and you do the test, okay, you will get 0, and then you will get the linear relationship, and the area under here is going to be external work. That is 1/2 time what? Time P and time delta. And you have the strain energy in this form as previously we need to determine the M, right? So we cut the beam for this distance of X. And if you summation of moment equal to 0, and this moment is positive, so your moment is going to be P times X. Since it's rotate, since they rotate in the same direction, so you move it in another direction, you will get, let me put it like this, you will get M plus Px equal to 0. When you move it into the different side, okay, it's going to be minus M equal to minus Px. Then you get M minus Px. You put it over there. Okay, now what you have is you deal with the integration. You just move the constant out. So this P minus Px square, this is going to produce the positive. Minus times minus is positive. So this is P square divided by 2EI. That's a constant. That is X square. So it's going to be X cubed divided by 3. And from where? From 0 to L. And then you got this P square, and L cubed divided by 6EI. And then you have this portion, okay, and all of them, when you push it, this is going to be the same value, right? You're going to put them together, this one to this one, and then you have what? You have this equation. By doing this equation, you can what? You can just do manipulate what we have. We have P, right? The P, test the P out. That P square going to be P, and this one cuts. This one going to change to 3. So this one going to have the equation from the deflection as the NA of PL cubed over 3EI. We have discussion about this before from the even the first one. We use the double integration method, and then we get this result. Okay. The problem is this is seemingly easy to use, right? But if the beam subjected to more than one load, if you have many loads, what we have is you're going to have many unknown delta. Okay. You have 3 force, you need to have 3 delta. So if you have that, you cannot solve equation by the principle of conservation of energy directly, because the equation just provide you one equation. So more development is needed. That's John Bunnery do some modification of this principle, and he arrived at the method of virtual work, which was very beautiful to use, even though it's the beam, it's the truss, or even though it's the frame. Okay, this is compared to the result that we have. Sorry, it's in Thai, but you may recall we have this equation from the double integration method. Okay, now we arrive at the principle of virtual work. The John Bernoulli, he developed this method about 300 years ago, since 1717, and sometimes this method called the unit load method, because John Bernoulli used the assumed unit load method to help him to find the deflection on the slope of the structure. That's the name of unit load method come from. Some people like to call it unit load method. Okay, unit load method. And let us just come to consider the beam. This beam, this elastic beam, is in equilibrium. That means it's static. It won't move under the force. And let us consider the case when we like to determine the deflection at sea. Okay, under any kind of force, this neutral axis is the represent to the elastic curve gonna deflect like this. Okay, when it's deflect like this, don't worry. What we have is the force going to produce this delta C. This delta C is the real deflection. Okay, and then Jarvis said, if you like to find delta C, you put 1.0 unit load. I said that's the name unit load come from at this point, and you consider the force, okay, time delta C. Okay, it seems like when the force just moved delta C, and then you got this is 1.0 time delta C. And he said this can be considered as the external virtual work. It's a work because it's a force times the displacement. Okay, and since the force is assumed, this is assumed. Okay, so the work is virtual work, and since it's external of the beam, so it's external virtual work. And then he said, this unit load gonna produce, okay, gonna produce something that's cause the force, okay, here, okay, the 1.0 produce cause the force here. And he also said under the real load is going to have the deformation dl here. And he said, okay, if that's the case, the external virtual work is going to be equal to the internal virtual work. So what is the work? Now, the work is going to be the force U here due to the assumed 1.0 unit. Okay, it's going to be U. Okay, and then it's going to have what? It's going to have the deformation of that element of the beam. It's going to have the dl. Okay, and since this is a beam, the whole beam, you got to do the whole integration. So by doing this, you got the what's so called the virtual work equation. This is called the virtual work equation that can be used, okay, to find the slope and to find the deflection of the beam, of the truss, and of the frame. Okay, in case you find the slope, you just change, okay, the one. This is one is the form of kilonewton. You must change this one for the 1.0 kilonewton meter. That is the moment. And going to time theta. Okay, let's say at point C. And that is going to be the integration of u due to this moment. Let's say it's called u sub theta and time dl. That is equation that you may use to find the slope. Okay, the slope going to involve with the moment, and the displacement, the linear displacement, going to involve with the force. Okay, that's what we have by this theory, and you may study this thing by yourself, and finally you will get what I just explained to you, and then you arrive at what we have, okay, as the virtual work equation. Let's call again. This is called sorry for this. The virtual work equation. And then let me consider again. This is assume load. This assume load produce internal force or internal moment. And then this is the real displacement. This is the real deformation. When the force and the displacement interact together, it's going to be the work. And if the force is assumed, so the work is virtual. And since this involved with the external, okay, we call it external virtual work. And then this also due to the assumed force, okay, that's time the real displacement. That's also the virtual work. However, this one happened inside the structure, so this part is the internal virtual work. Okay, and then you have this as the conclusion for the theory that we have. And similarly, if we require to determine the slope, as I just mentioned before, when talking about the slope, that means it's going to relate to assumed moment. Okay, assumed moment. And then you may have this equation that is virtual work and virtual internal moment. And it's going to be the actual rotation and actual deformation due to the actual applied loading. Okay, in conclusion, if we require to determine the deflection of the beam, from the principle of conservation of energy for the structure that is in equilibrium, external work due to virtual unit load, gonna equal to internal energy due to that virtual unit load. That's 1 kilonewton or 1 kilonewton meter. That's the name of unit load come from. Okay, that's the name of unit load come from for the one over here. Okay, and then you have this, and then you have this, and then you have this, and then you have this. As I just mentioned before, you just go back and try review what I do explain to you. Okay, and for the slope, you have this. Okay, and then you can determine what we determine this one. You only can determine this one from the structure that's subjected to the virtual load. Okay, this is for the virtual load. Okay, and you compute this for the real structure or the from the actual load. Okay, that's for the actual load. It's going to be very easy. For example, if it's in axial load, you have it for what? Delta or dl equal to nl over ae. Okay, if this is for the bending, this is dl. This is dl is going to be it's going to be d theta. It's going to be rotation. Okay, it's going to be m over ei and time dx. We will talk about this later. Not that hard. Okay, now we're going to apply our knowledge of principle of virtual work to determine the displacement of the truss. Before this, you got to understand how truss perform when it's subjected to the force. Okay, the truss, this truss has the support of pin here. So if this is point B, so the deflection at B in horizontal direction is going to be equal to the deflection SB in the vertical direction, that is equal to 0. This is a roller, so the deflection, let's say this is C in the vertical direction going to be 0. However, the deflection at C in the horizontal direction is going to be something because it's a roller, it can move. Okay, and for any free joint here, there is going to be two displacement for any given joints. Okay, in which it's going to be, let's say A, it's going to be phi sub A horizontal direction and phi sub A in vertical direction. So for a joint, okay, for a joint, we have two displacements. And what it means is over here is going to have both in the vertical, okay, and also in the horizontal. So the structure under force here actually is going to move. If I be the analyzer, I'm going to put this a little bit more, and this is a little bit less, and then the deformation of this truss gonna be something like this for the bottom chord. And for the top chord, since this one is down, it's going to be down, okay, very close in the deformation. And this one also be down. And then the deformation here. You just connect the joints here and over here is maybe move about here. And then the vertical. And then the vertical. And then the diagonal. Okay, this is may call the elastic curve of the truss. And if you like to find the vertical, let's say the vertical displacement at A, so you put the force, 1 point unit force at A in that vertical direction. And now what we have is the external virtual work is going to be equal to internal virtual work. Okay, and what we have is the assumed 1 unit force is here. So the assumed 1 unit force, let's say in 1 kilonewton, if you like, is gonna time the, let's call it V, okay, sub C, V sub A, and in vertical direction, in V sub A and vertical direction, That is going to be equal to what for this? Equal to what we have is the 1 point unit force going to act here, and it's going to produce the normal axial force in this beam. Okay, let's call it n sub v I, when I is the number of element, number 1, number 2, number 3, number 4, number 5, number 6, 7, 8, and 9. Okay, that's each member gonna have the axial force. And then if this axial force times the deformation of each element, you're going to get the internal virtual work. So n sub vi. Okay, it's gonna time the deformation of each member. It's gonna time, let me call it dl sub I. And since there are total of 9 members, so you got to summation of I equal to 1 until 9. And now, what is this? This is the deformation of the member due to the F pilot. Okay, if you have one of this member, let's say, and then this is number 2, right? This is number 2. So the force over here gonna be what? The force number here due to what? Due to the pi force. The pi force gonna produce n sub I. So this is gonna be n2. This is gonna be n2. And what we have is, we have the sigma equal to E times 10. And we have n sub I over A sub I equal to E sub I. And then D sub Li divided by L sub I. Every member have their own Hooke's law. Okay, and if you like this, D sub Li is here, is going to be n sub I Li, n sub I Li. You take this one down, divided by Ai and Ei. And if you put it over here, okay, this one gonna be n sub I Li divided by Ai and Ei. That is going to be the what's so-called the virtual work equation. This is going to be the virtual work equation for Truss. Okay, for Truss. Okay, you can record it. From the principle of virtual work, we have this. 1 unit force is applied to the point that we are looking for to the delta, and 1 unit point produce the internal force du, and then the deformation, okay, here is real, and this is going to produce the external virtual work, assume time the real, and then the internal force due to assume 1 unit force gonna time the real deformation. What is going to be this? And then again we have this dl equal to nl over ae. Put it over here, and then you got this. Okay, and don't forget there are a number of members, so it's going to be n for v I times n I l I divided by ai ei if each member have different material. Okay, that is not real. No one gonna produce the truss with member with steel, another member with aluminum, another member with copper, another member with brass. Okay, no one gonna produce those kind of truss. So most of the time, E of the truss, every member of the truss is going to be the same. Okay, and now we can conclude that 1 is the virtual unit load. Okay, that is what? That is going to act at A okay, in the direction of the design deflection in the vertical direction. And n, small n is the forces in the truss member due to the virtual unit load. And then capital N is the force in the truss member, but this time due to the force, due to the real force. And then A, you know that, sorry, this is going to be the area. Okay, this is the area. And this is going to be modulus of elasticity. Now, let's conclude it. So most of the time they have a 3 big steps of determining the first one. The first one, you're going to consider the deformation of the truss, okay, and formulate the virtual work equation. This is kind of a general words for the first step. That means you see this deformation that I considered before, you arrive at the virtual work equation. And from this equation, the second one, you will find the member force, forces, okay, which is going to be n sub I, capital N sub I due to the actual load, and the small n sub I, which is due to the virtual force. And the third, you find what you like to find. This one, you find delta for this problem, and delta at what? Delta SA in the vertical direction. Okay, so don't confuse. Sometimes I use delta, sometimes I use V. It's going to be the same. Okay, when you type in computer, it's going to be really nice to have the delta, and when you write it by hand, I sometimes prefer to put it at V. Okay, that is everything we have analyzed for the n, and then analyze for capital N, analyze for the small n, and then put it back into the virtual work equation, and then you get the result. Okay, we have some problem that we going to work on and let you guys to understand it. The first one is the truss. This truss has different area. It has different cross-section area between the top chord and the but top chord not the same. They are different from the vertical chord and the diagonal. They like us to determine the what B, the vertical displacement at B. So first we're going to consider how this truss going to deform under the force. Okay, this is going to deform like this. When it's deformed, you just imagine it. Okay, just imagine it. When you push like this, C going to be down here, and also B going to be somewhere down here. It's moved due to the force. Okay, when this element move, the author, this is the pin, is one move, both x and y direction. The A also. If the A and the one move, okay, it said V sub dH equal to V sub dV is 0, and V sub AH equal to V sub AV equal to 0. It will move. So this is gonna move to, you got to draw the straight line. Put your ruler and connect the joints together, and you can see some element is in tension. Example, this one supposed to be in tension. Some element could be in compression. Sure, this one in compression. And then you may have this one, V sub C vertical, and this one V sub C horizontal, the same one as here. Okay, this is gonna be V sub B vertical, and small distance here, V sub B horizontal. Each joint of the task gonna have two displacement, one horizontal, another one is vertical. And now we come to the virtual work equation. External virtual work, okay, is gonna be equal to internal virtual work. And now what we have is this one going to subjected to the what, the force at B also. You got to put, okay, the force of 1 unit at point B. Put it at point B. At point B. 1 unit in the vertical direction. Now, this 1.0 force, okay, is gonna have the B sub V sub deflection SB vertical. Okay, it's going to have V at B vertical, and it's going to equal to the summation. The summation of what? Summation of the force due to this one unit. Okay, this one unit gonna produce N, okay, sub V I. So this is N sub Vi. That's cause the force inside this is not real, and it's gonna have the deformation of each member of the task. Okay, that means it's gonna have capital N I L I over A I, and this one produced by the same E. Just put E. Okay, and then you arrive at this equation. Now, this is the first step. Okay, as I just write before, I do not like it. Okay, just go back to the previous slide. The first one is consider the deformation of the task and formulate the virtual work equation. That's already we have this. And next one, we determine N here. Okay, capital N, the force due to the actual load. Okay, and then we determine this one, the force due to the 1 unit load there. Now, deformation here, just put it here. So determine it. Okay, if you see this cantilever thrust, cantilever thrust, we do not need to determine the reaction. Okay, no need to the reaction. And you also need to apply some important thing, zero force member. Can you see? Member. Can you see which member going to be the zero force member? That is two row. One is two joints, join together. Is two member, join together at a joint and no force. That's two members going to be zero force member. If there is three members joined together and two of them in parallel and no force acting at the joint, the third element gonna have zero force member. So this is easy. This is zero. This is zero. Okay. When these two is zero, so we come to the joint C. We come to the joint C. We have this one for the X. We have this one for the Y. See, and you have two members. For the member AC, member AC have this direction. Okay, and under the application of the force here of 22.5 kilonewton, what do you think? This one contribute this upward to C or in opposite direction? You may trying to understand this problem. Okay, this problem, if you like to balance it, you need to have this component of the force. So this one supposed to act in this direction, and we call this F sub AC. Okay, AC, and F sub AC has the ratio of what? This is 0.9, this is 1.2, and if you put it, it's going to be 3 and 4 and 5. So this is going to be 3, 4 and 5. If this force is in this direction, if you put this one in in the horizontal direction, this one gonna put in this direction, and what we have is the force here must act in this opposite direction. So this is gonna be F sub CD. Okay, and now that is the joint C, the free body diagram of joint C. So from the method of joints, we should use which one first? Summation of x sub x equal to 0 or summation of f sub y equal to 0. If you put them in the x, you will get two unknown, and you didn't get the result yet. So we're going to put the first one for summation of f sub y equal to 0. Just put this one up. And then what we have, this is going to be F sub AC, you put in vertical direction. That's going to be 3 divided by 5. So this one up. You may have this one for 0.5 F 0.6 F sub AC is up. And then it's going to equal to the force of 22.5. Okay. And then your F sub AC gonna be F sub AC gonna be 22.5, and then you're gonna divide it by 0.6, and then you get it for what? 20.5 divided by 0.6, 37.5. So this is gonna be equal to 37.5 kilonewton. Okay, this is the first one, and it's going to be in compression, though it's minus 37.5 kilonewton. And now for F sub CD, it's going to be this F sub CD going to be positive. So F sub CD is going to be equal to this one, 37.5. You have 37.5. 37.5. This time is going to time 4 divided by 5. So time 4 divided by 5. What you have is going to be time 0.8. So it's going to be 30. This one going to be equal to 30 kilonewton. And it's going to be in tension. This one going to be in compression. So this one going to be plus 30. Okay, that's we have for all the member. Okay, we have the result of our Truss analysis here. And if you check, you may check by divide the force by the given area. You may have the Truss have the stress less than the yielding stress. So it's okay. It follow our assumption that member going to have the linear elastic behavior, and also the deformation going to be very small. Now, we put the 1 unit force here, and then we're going to analyze this structure. Okay, and if you see here 1 point unit load here, and then you have this one for x, and this one for y, and then you have this one 1.2. What we have? We have this is going to be F sub BC, and also we're going to have this one for F sub AB. And if you summation of x sub x equal to 0, you may get F sub AB equal to 0. And if you have summation of F sub y equal to 0, so upward is positive. So f sub bc gonna be 1.0. Okay, and then this one gonna be the f sub bc. Okay, and this one gonna be f sub bc. And if you put the joint c over here, the joint c gonna subject to this force of 1.0. Okay, this is 1.0, this is going to be 1.0, this is 1.0, this is 1.0, this is joint C. And then you have this one for X, and then you have this one for Y. And now you have member AC again. Okay, and what you have is going to have this member. Okay, this is going to be F sub AC. Okay, and it's going to be up, right? Because it's going to resist this one. And also you may have this one for F sub CD. And if you consider this free body diagram, okay, and you may also notice that this going to have this is going to have the ratio of what? Ratio of 3, 4, 5. This one going to be very similar to the free body diagram here. They are going to be the same actually. By the force here 22.5, but change to the force here of 1.0. So now we will have this one for minus 37.5 divided by 22.5. Okay, and we have this one for 1.0, and is in tension. This is plus, and we have this one for plus 30 and divided by 22.5. Okay, that's help. And if you like, you may do the proof for this by the same calculation procedure that we have before, and then you may have the result as I just mentioned here. Now what we have is we have the n sub I. This is for the capital N sub I, and this one for the small n vertical sub I. And now we're ready to put everything together. Okay, and what we should do is just put everything in the table form, because we are going to have many members. This task is easy, just have 4 members. Some tasks may have 20 members. You're going to put everything in the table. But in examination, I just put just 5, 6, 7, or 8 or 9 members, not more than that. Okay, now just put the member AC. What is AC? AC is here. AC is here. Okay, AC. It has the length of this one. It has the length of 0.9, and this is what 1,500. It has the area here. Okay, area here. If you notice before, this is going to be minus 37.5, and this is going to be minus. This is minus. It's supposed to be here. Okay, this is going to be here. Okay, and the calculation going to be here. And then DC is on the top. Oh yeah, DC is on the top here. Okay, it's 1,200 millimeter, and the A is going to be here 1,250, and the N is going to be here, put to here, and small n going to be here, put to here. Okay, and then you can calculate for this. And the other A, B, C, D, you can go as before, and force going to be 0 and 0. And now, if you have 1 0 here, just put 0 here. If you have 0 here, just put 0 here. That is going to have no calculation. And now, you get the total of this. So most of the time, you got to put this one into the summation over here. Then what you get is going to be the 0.94 millimeter. And since it's putting positive, when it's positive, that means it's going to get the same direction as the 1.0 unit. It's going to be the one that indicates the direction of the displacement. Okay, and then we get the result. Okay, in conclusion, you get that easily. You get this, right? About horizontal. Okay, if you like to determine the horizontal displacement here, what you need to go back, you just go back to the problem, but now you just determine it subjected to the force here. Sorry. Okay, let's just put the force here. The force here just take out. This one just take out. The force going to be here. And then what we have is if the force acts here in the horizontal direction, this one going to be 0. Okay, if this one is 0, for the 0 force member, this is 0, this is 0. And this is going to be just 1.0, only this member. Okay, and then when it's come to the table, you may have the force here as before, but this time, this one just change into this. Okay, this one going to be past 1.0. So this is 0, this is 0, this is 0. This is the same. Okay, you have just member AB. Your member AB gonna have what? Part 1.0. Okay, and the other is 0, 0, and 0. So by doing this is 0, this is 0. Since this has no force here, so everything is 0. So the deflection, okay, at point B in the horizontal direction gonna equal to summation of 0. So actually, what I draw here is not that's correct. Okay, this point have no. Okay, just have only V sub BV. Okay, but V sub BH gonna be 0. And then you got the deformation of this Truss correctly like this. This is not correct. Just put this one into this one, and the result is more accurate than before if you can determine this. Okay, just try to slowly taking calculation by yourself. It's not that hard. Next, what's going to happen if the 22.5 kilonewton change to 45? Since the behavior is linear elastic, okay, you will see that things just get the double. That means the deflection going to be the double. The force here actually, to be correct, this one gonna time 2, this one gonna time 2. Okay, and that means the deflection here gonna be time 2 to be this, and you get everything. The stress will be in linear elastic. Okay, now we finish the first problem. Let us have another problem. Okay, let us consider this Truss. Now we are going to determine the vertical and the horizontal displacement, okay, at joist B of the Truss. But this Truss have equal A and E. This set AE, which is the axial stiffness of the Truss member. Okay, this is going to be equal to constant. The example before that, the AE is not constant, but this one is constant. Now, what we have is the first one. First one, we consider the elastic curve of the truss, okay, and then formulate. First one, we consider the elastic curve of the truss and formulate what? The virtual work, formulate the virtual work, formulate the virtual work equation. That's the first step. This one going to be what? This is B, right? This is the form more, this one we form less, and this one may have moved here, okay, due to the application of 30 kilonewton. So this one also move here, this one also move here. So your deformation, this one gonna have both V sub B H, okay, and V sub B V C also V sub C H and deflection C V, and then you get this kind of deformation of the structure, okay, and you may also have V sub D H, okay, equal to something, but V sub dV is 0. That's the vertical direction. And also you may consider V sub A H equal to V sub A V equal to 0. Each node of the truss have two deformation, okay, one is in the horizontal, another one in the vertical, and then you can put it like that easily. Now you're going to determine the what? The deflection at what? At point B in the vertical direction. So for the concept, just put them in the concept first. So we are in to put this truss and put this pin, push this roller, and the force of 1.0 is here. And now for this, you got to have 1.0 with the V sub BV. Okay, time V sub B vertical, and this is going to be equal to the summation. This is going to be the summation. Okay, summation of what? Summation. This one gonna produce the N sub B V I. Okay, this is gonna be N, the force in each member due to the 1 unit load at B in the vertical direction. And this one gonna produce the N sub I. Okay, this one will be N sub I, and then it's gonna time N sub I, and then what we have is L sub I divided by A sub I and E sub I. Okay, that is for the vertical displacement at B. Now, if you consider the horizontal displacement at B, now you do the same thing. Okay, we draw this one. That's me elast this one. This is too much. Okay, this is the roller, and this is the pin. Now this is point B, so you put this point B in the horizontal direction. Okay, you're going to get this truss. So now 1.0 again, time what? Time deflection SB horizontal direction, this one, and this is going to be equal to the summation. This is going to produce what? This is going to produce n sub bhi. So n sub bhi, and then it's going to have n sub I. Yeah, n sub I over here. We'll have n sub I here. Have n sub I. Then you can have L sub I divided I sub I and E sub I. That is the concept that we are going to solve this equation to get the deflection as may required. Now, the picture shown here is the result from the analysis of computer program. And then you may see what we have is BH is going to be about the difference between here and the BV going to be in the vertical direction. Okay, and the same thing as this vertical CH is going to be about here, and vertical CV is going to be about here. Even though this V sub DH is going to be, okay, the distance here. You can calculate everything if you like. Just put the unit load in that position in the direction you like to determine. Okay, now let's see. This time I won't solve the capital N for you, but from the computer program we will set, we have, okay, the result like this. And the result, when you have, you got to see this is going to be plus 20, this is going to be plus 10, this is plus 10. You got to separate between tension and compression. On the top, this one is minus 20, this one is minus 28.284. okay, the plus is tension and the minus is going to be in compression. Everything you got to indicate it, review it. And for capital N, this time you may notice that the 30 kilonewton and the 1 kilonewton, they are in the same point at the same direction, but the value is 30 times different. So if you know this capital N, so the small n gonna be n sub I gonna be capital N divided by 30, and then you get the result. Okay, the result. Now you get the whole result and do the same thing, taking all of them into the table, and don't forget about the sign, the positive and the negative. And also you should check, okay, positive times positive is positive, negative times negative is positive, author going to be negative. Okay, and then you get this, and then you get the result of 3.9.694, and then you divide it by AE, you get the result. Since it's positive, so this is going to be downward 5.2 millimeter. Okay, it's going to be downward 0.2 millimeter, you know that, and it's going to show you here with 1 point, to here with the vertical. This is 5.2 millimeter. And now we are looking for this one, okay, deflection SB horizontal direction. Now we can go it really easily. Okay, before going to the B sub H, they are asking us if they like to control the deflection, to limit it, not 5.2, just limit it to 4 millimeter, or limit it to just this 1 meter. They ask us to determine the A. So the concept is they're going to limit the deflection, so the A is going to be larger. Previously it's 300, right? And then you can put this one and do everything, and especially you compute by kilonewton, so the E is going to be power 6 kilonewton per square meter. and this is going to be in meter. So it's going to have the section of 387.1 square millimeter, which is larger than before, right? Before we use is 300 millimeter. And you also can select the size of the truss by using the truss table. Okay, this time you get this. Sorry, some in Thai, I'm not changed it. Okay, now for horizontal displacement at joist B, okay, you do the analysis of n as before, capital N, due to the axial force. For the small n, this time it's going to put like here. Okay, if you put this one, for the free body diagram, this A sub y, and this one going to be D sub y. We're going to determine the N, B, H sub I. Okay, so we first start by finding reaction, and then we also have A sub x. If you summation of moment about A equal to 0, take moment here, you may have D sub y equal to 0 because there is no also vertical force. And then you also F sub y equal to 0, A sub y equal to 0. So this is 0 and this is 0. Only the summation of x sub x equal to 0. You have A sub x equal to 1.0 of this. Okay, and now you can do the analysis of this task by using the concept of zero force member. Okay, this point has the zero force here, so this is 0, this is 0. And again, this is going to be just only 2 points. This is 0, this is 0. And again, this is 0, this is 0, this is 0, this is 0. And you can see this is going to be plus 1.2. That is going to be N sub BH sub I. Only one element going to be there. Okay, that is going to be the same what we have. Then we put everything into your calculator, and we have only one law that's going to produce the number. It's going to be 60, and the horizontal displacement at B is going to be 1 millimeter. 1 millimeter. Okay, and it's positive. That means it's going to put in this direction. Okay, and it's shown here. It's shown here. And if you like to determine the C, okay, you can find, right? It will be very easy to find it. This is going to be the resultant of both the vertical and horizontal. Since the displacement is the vector, you can find the resultant of the displacement here. Okay, horizontal at C, N is the same, but this time it's changed to this. But do the same thing. This one gonna be 1.0. This is 0. This is 0. So this is 0. This is 0. And using the zero force member, 3 member, okay, connect together. What we have is summation. This is 0, 0, 0, 0, 0. So this is plus 1, and this is going to be plus 1. So this time you have 2 rows that have the number. Okay, that is going to be the new row of this one. You time it, and this time you get it for 30. Okay, you got it 90. And if you prefer and you go back, if you determine the delta at the h, that means you're going to push this one into here. So this one going to be plus 1, this one plus 1, this one going to be plus 1 also. So this time could get 3 line. Okay, and then if you do it, this one change to 1. Okay, this is going to be 30. So it's going to be 120 for that. It's going to be 120. Okay, just change it to 120. So delta sub CB, delta sub C sub BH is 60 over AE. Delta sub CH is 90. Delta sub DH is 120 divided by EI. So the magnitude just increase from delta sub AH equal to 0. And then 60 over EI 90, sorry, 60 over AE, 90 over AE, and 100. That's all point up to the light. Okay, that is an example that's for the task subjected to the loading. Okay, and now there is two more things. One is the task that's subjected to the temperature change, and the last one is the task that's subjected to fabrication error. Okay, let me start by the temperature change. In the roof, okay, during the daytime, the member of the task subjected to the hot temperature from the sunshine. Okay, and then you know that if you have the member that you put it, okay, and the temperature increase, most of the material will expand. Okay, it will expand, and the deformation due to temperature can be computed by this equation. This is coefficient of temperature change, coefficient of expansion due to the temperature change. Okay, this is the length. This is the length of L, and this is the change in temperature. Now, what we have is coefficient of thermal expansion for the task member for alpha, and for the L is the length, and for the delta T. Okay, and what we have is what? When this one is expand due to the plus, and then point E and point F, they won't like it to expand. What is this? It won't expand. It won't allow to expand. When it won't allow to expand, what happens is this member will subjected to this force. And by the third law of Newton, this is going to push this guy like this. Okay. When it's put this guy like this, what happened is this point gonna move. Okay, like this. This point also gonna move like this. When this point move like this triangle, okay, they're gonna move like this. And this is gonna connect. And this is also gonna move like this. And then your task is gonna defect like this. Okay, most of the time when the roof heat up, the member on the top chord, okay, gonna expand, and then it's going to lift the task up. That's good because it's going to resist the deformation of the task due to the dead load or even the life load. Okay, now what we have is, if you like to determine the deflection at some point of the task due to this, let's say if you're interested in it. So by doing that, by the principle of virtual work, you may again, okay, like the external virtual work. Due to what? Due to the temperature change, okay, due to delta T is going to be equal to internal virtual work, okay, due to unit load. Okay, that's it. Sorry, due to the delta T and unit load. Okay, and this is going to be internal virtual work due to delta T and unit load. What we have is we're going to put the 1 unit point at B. Now this 1 unit gonna time the VB vertical. So this is going to be assumed load times the real deflection is going to be equal to summation this will produce the force inside it. Okay, this is D sub V, let's say BV. This is going to be N sub V V and I. And it's going to have the deformation occur here. Since the deformation occur here is this, so it's going to have alpha L delta T. So you got the virtual work equation that's in the form over here. Okay, this time the dl is in this form, unlike before that. Before that, dl is going to be nl over ae. This is due to the load. Okay, this is due to the temperature change. Okay, part of this equation is due to the unit load, the 1 and the small n. Okay, and part of this equation is due to the actual load, is the diffraction. Okay, and the diffraction and the temperature change. The coefficient of thermal expansion is vary with the material. For steel is 12 times minus 6 per degree Celsius. For the aluminum, it's a little bit larger, 2 times. Okay, and it should note that the concrete and the steel have very similar coefficient of thermal expansion. So under the application of the force, the reinforced concrete, the material in reinforced concrete, they are going to be very compatible. Okay, now to our point, we do the formulation already, and let's say the temperature at this portion of the loop just get hotter now, as you have before. Okay, you have what? You have to determine the force. Okay, small n. Okay, there is no n, n is 0. For the small n, you put the force here. Okay, force what? At point B, as point B, sorry, this is wrong, as point B in the vertical direction. Okay, and then this is going to be N sub B vertical direction I. And you may see we have only one member that's hot, that is the Fe. So the N sub BVI over here is going to be N sub BV, only N due to this member, N sub Fe. Okay, and then the L is going to be 3 meter. Delta T is going to be 30 degrees Celsius. It's just only one member, right? And this is 12 minus 6. 12, 10 minus 6, okay, per degree Celsius. You put them together, you get this as the deformation, the vertical displacement at B due to the temperature change for the member DE. And it has a negative, okay? That means it's going to be in the opposite direction of unit load. Okay, as I said before, the temperature change, the hot surface of the loop help the Truss to deflect upward. That's help to reduce the deflection due to the lead load and black load, or the gravity load. Okay. If there is temperature change in 3 member, so don't worry if it's in 3 member. You put this one as the N sub AF. You put this one as N sub Fe. You put this one as N sub ED. Okay, and alpha delta T L is different. L sub AF is within the length of this. Okay, L sub Fe, this is 3 meter, and this is going to be equal to L sub AF. You put them together and then you do the calculation. This time the Truss move up for 2.88 millimeter due to the temperature change of this 3 member. Okay, it gets a little bit larger than before. Now it's put upward. Okay, and for the verification error, sometimes there is the error in the construction. This is too long, right? This is too long for what? For 0.001. So you got to push it up. Okay, push it to get it to the correct length. This is too long. Okay, this is positive. This is too long. So you got, if it's too long, put that. So this task going to subject that to the force like this. That means what? The B gonna move here, the E gonna move here. So what we have is this one going to move to a given position. Okay, this is going to get longer, and this one gonna move like this, and your task gonna have the elastic curve like this. And then we have is what? You're going to have 1.0 time v sub b vertical. That is going to have what? You got to have this task again, and then put the same thing of unit load to the task, okay, to the task, and then you time this by v sub bv. That's going to be summation of the force of n sub v as before, and time this one is dl. You can put this one directly into this equation because it's the length already. Okay, and then your equation gonna be like this. So if this one, sorry, this is bv, if this one bv, if you like to have this one is bv and this one is bv, this one going to be n what? Only n for dash member is going to be n sub be only. Okay, because only be has delta L, the other won't. Okay, and now we have to put one unit load to the point of our interest in the desired direction, and then you got to determine the internal for task member due to that unit load. That is going to be small n. So and delta L already know from the fabrication. Now you put like this. So this equation is going to be delta B vertical. Okay, and then there is no capital N, just the small n. Small n going to be in the member BE. Okay, this is going to be, take this one, just one member. So n sub BE and delta BE. Very easy, right? So you just put this one, the n sub BE is 0.471. And then you put into your equation. You get what you have is 4.7. That means what? That means it's going to be downward, this one 4.7. So fabrication error gonna increase this, in this case, increase the deflection of the dead load and live load. Okay, and finally, if you put them together, okay, you may get the total effect of applied force. Okay, effect of temperature change, effect of fabrication error, and the resultant of vertical displacement SB is going to be 9.2. And if you divide it, if you find the ratio of the span per deflection, it's going to be 978.3. That is going to be larger than the allowable, which usually we have the ratio of this is going to be 360. Okay, if there is there has no wall under the beam. But for the task, usually we're going to set the deflection very large because the span of the task usually very long. So when they design the task, you must control the deflection of the task as small as possible. Okay, usually it's not 360. Like you design the 10 meter. Okay, 10 meter. If you say 10 meter span, okay, task. And then if you use 350, that is going to be 10,000 millimeter divided by 360. Your task going to deform 27. Okay, that is going to be deformed 27.8 millimeter. That's maybe you may use it depends on your judgment. If about 3 centimeter is okay, it's okay. But if it's large, you can control it by deciding it with the larger section. Okay, that is the method of virtual work for the task, and I will have some demonstration problem to you, and after that we will have this method of virtual work for the beam and then for the frame. Okay, that is the end of this clip. Bye bye.